Okay, so I guess we're all happy to start the afternoon session with Evdokia and Nikolova's talk on algorithms for risk mitigation and analysis.
Very much, Yuval. So again, I'm Evdokia Nikolova. I'm an assistant professor at the University of Texas at Austin. I'll talk about algorithms for risk mitigation in networks. And here is my motivation. The main thesis of this talk will be that uncertainty and risk can dramatically change the design of algorithms and also tools for analysis of algorithmic game theory and mechanism design. For example, in the context of transportation networks, we may need fundamentally different algorithms for computing what is the optimal route when the decision maker or driver is risk averse. In corresponding algorithmic game theory models, congestion games which model multiple drivers, let's say, may need fundamentally different tools for analysis. In terms of what is the resulting equilibrium or traffic assignment in the network, and consequently the resulting congestion. And consequently, then, we may need to revisit what is an elegant theory of optimal tolls, which is one way for alleviating congestion. And all of these models, even if they are theoretical abstractions and not precisely reality, are still essential to understand to give us some hope to tackle what is now one of the grand challenges of our present-day society, that of traffic congestion, which was measured to be $126 billion in just highway congestion cost in 2013, and is projected to increase by another 50% by the year 2030. And so this is the structure of my talk. I'll have three main topics. First, I'll tell you what I mean by risk and what are different approaches to modeling and defining risk aversion. And then I'll tell you about the design of algorithms for risk-averse decision makers, and then algorithmic game theory models and analysis when we have multiple risk-averse decision makers interacting with each other, and conclude with some open directions. So what is risk? Although everybody somehow knows what risk is, there is no one clear mathematical agreed upon definition of risk. Instead, there are multiple approaches that were developed independently. The main one from economics, which models risk-averse decision makers, is known as expected utility theory. And this is still a prevalent theory, very widely used, although it has its criticisms and now has various alternatives. In finance, orthogonally, we have the Markowitz mean-variance framework and related frameworks. And recently, now we have seen a development of a modern risk theory. So I'll very briefly mention a little more detail on these three approaches. I will not talk about systemic risk, so I will be mostly talking about risk from the point of view of an individual decision maker, such as an individual driver trying to get to the airport on time. Systemic risk is something also really important and interesting to me, and also very important to, I believe, a variety of problems we look at in engineering, computer science, and natural sciences, but still I don't understand it very well. It's something I hope to understand a little better in the future, and for now I just give a pointer to a very long 100-page survey by people in finance. Also, something else I will not talk about is the notion of dynamic or multi-period risk, which is again, very important to dynamic and real-time decision-making problems. But again, I hope that we can gain a better understanding of that in the future. So expected utility theory postulates that risk preferences can be represented by a utility function, which is essentially a function from random variables to real numbers. It says that an individual prefers random variable x to random variable y, or lottery x to lottery y, as is termed in economics, if and only if their expected utility for this random variable is greater than or equal to the expected utility of that random variable. And so this theory essentially compresses random variables to numbers because we really only know how to compare numbers. And so from there on, decision making comes down to working with those single numbers. And now that's a prescriptive theory, not necessarily descriptive, in the sense that it is built on two axioms, independence and continuity, which have been shown to not necessarily hold in practice. Nevertheless, it's still a very useful, very prevalent theory of decision making. And I just mentioned here now that there are also many other alternatives, such as ambiguity theory, prospect theory, and so on. Again, I point to this survey for the alternative theories. Orthogonally, Markowitz in 1952 is viewed as the first one to quantify risk in the context of portfolio optimization in finance. And he postulated that risk should be represented by the variance of a portfolio. And as such, decision-making, a decision under uncertainty, can be seen as the trade-off between risk and reward in those various different models. So I've just written down the equivalents in optimization theory. Constrained optimization, which would be, for example, maximizing our return subject to a budget on the variance, so maximum on the variance or the risk that we can handle. In unconstrained optimization, we can view this framework as optimizing a linear combination of risk and return. For example, maximize our return minus some multiple times the variance. We can also view the problem as a multi-criteria optimization problem, where we don't really know our trade-off between, our desired trade-off between risk and reward, but we are interested in all the non-dominated risk-reward pairs. This is defined as the Pareto frontier or efficient mean-variance frontier in finance. Something that also belongs to this mean-variance framework is the concept of value at risk, which is essentially the alpha quantile of the distribution of a random variable, and it's widely used in finance now for measuring the risk of various financial positions. Something else in optimization that's related to this framework is that of chance constraints. So that's an optimization problem in which we have this random variable x, and one of the constraints is a soft constraint in the sense that we want the probability that our random variable exceeds some given budget c is at least some given desired probability alpha. So some of the criticisms of this overall Markowitz mean-variance framework are that it may lead to non-monotone outcomes or decisions. For example, since I'll be talking about transportation as an example, let me say if we're choosing between two routes, one that always takes 1 hour to reach the airport, another one that always takes 1 hour or 50 minutes, clearly the first one dominates the second one, but this framework may penalize the second one because it has a positive variance, and so it may prefer the first one that always takes 1 hour. So I mentioned that because it's a known drawback, but it may or may not be a drawback in the context of transportation or other non-financial situations where certainty has its value. Also, some of those outcomes of the mean-variance framework are that it may lead to non-convexity. So some of those, for example, value at risk or chance constraints are very well-known non-convex problems. Whereas one may argue that a reasonable risk-averse decision maker should prefer convex positions. So the convex combination of two portfolios should be no worse than the individual portfolios. So because of the various drawbacks with this theory, a new theory was developed starting in 1999, so quite fairly recently with the work of Arzner et al., who said that we should assume an axiomatic approach to defining risk. So we should state down certain axioms that make sense, that risk-averse decision makers should satisfy, should have in mind. For example, monotonicity. If a given portfolio always gives us non-negative reward, then the risk should be less than or equal to 0. Similarly, convexity, which I mentioned already, and a few others. Some of the other axioms have been put into question whether we really need them or not. So without axiom 3, for example, risk measures that satisfy the remaining 3 axioms are called convex risk measures. So now there is a lot of research taken up by convex analysis researchers and finance people are on what are the properties of such convex or coherent risk measures, what are risk measures that satisfy these axioms, and so on. And I'll just mention one example of such a coherent risk measure is the conditional value at risk. So I mentioned the value at risk earlier, which is the percentile of a random variable. And the conditional value at risk is essentially the expectation of the tail of this random variable. So if we are thinking of an objective function which is getting to the airport on time, so we have a fixed budget and we really want to make the trip within 1 hour, otherwise we'll miss our plane. So we have a clear cut of penalty if we come after that 1 hour, the plane has left, so whether we are late by 1 minute or half an hour, we have an equal penalty. Well, conditional value at risk tells us that we should care about how much we are late. So instead of having just the same penalty for all the undesired events in the tail, we should take the expectation of the tail. And this is one such coherent risk measure. And one remark is that when x is a normally distributed random variable, both the value at risk, which is still very prevalent in finance, and the conditional value at risk, which so far has mostly been used in research and hasn't been adopted in practice, are equal to the mean minus k times standard deviation for appropriate constants k. And I mentioned that because this is one objective that I'll be using in some of the coming models. So what are the challenges of algorithms for risk-averse decision makers? And I'll come back again to routing and shortest paths. That's just one fundamental problem that everyone is familiar with. But more generally, if we consider a combinatorial problem where we are looking to get some feasible solution, for example, a path, that equals whose cost equals the sum of costs of individual elements, for example, the edges that make up the path. So if now instead we don't have given numbers for the costs of different elements, but instead we have random variables, for example, in transportation networks, we really don't know how much time it takes us to go from here to San Francisco. It's a random variable. So think of the travel time as those costs. Now, if we assume independent, random independent element costs, which will be one assumption that I'll use throughout the talk, not necessarily realistic, but a starting point, a risk-neutral solution doesn't care about the risk and just wants to measure the expectation of the solution. And by linearity of expectation, we can very easily reduce the stochastic problem to the corresponding deterministic problem. So a shortest path problem remains a shortest path problem with respect to the mean travel time of the edges. So nothing new there. We can just use the well-known algorithms. If now we make one step away from risk neutrality and want a risk-averse objective, for example, represented by an exponential utility function. So my objective is to minimize the expectation of the e to the power my travel time in this case. So we can view that as exponential utility or we can view it as what's known as entropic risk measure, which takes the log of this. So just mathematically, notice that this leads again to an additive separable problem, where the risk or utility associated with the entire path is just the sum of risks or utilities, or costs, I should say, of the individual edges or elements. And so again, we have reduced the problem to a standard deterministic problem. So again, we can apply the algorithms that we know. So beyond that, it has been observed time and again in the literature as now various folk theorems that if we deviate from the linear and exponential utility, pretty much every other utility cannot give us this nice additive form, and so we would, optimizing the expected utility in this case, would lead to a nonlinear or non-convex problem, which algorithmically becomes very different and we don't really know how to handle. I'll just mention again, this is under utility theory. If we think of the mean-variance framework, and again think of those as independent random variables, the variance of the sum of two independent random variables is the sum of the two variances. So again, we would have an additive problem. So if our criterion is mean plus variance, so minimize the mean plus variance of my path as a way of capturing risk, we would again come down to the familiar deterministic shortest path problem. But again, in most other instances, we would not. So what do we do in other instances beyond those 2 or 3 simple objective functions? So the challenge here becomes that, for example, in shortest paths, since I'm mentioning how things become different from the deterministic setting, the optimal substructure, a property that allows us to use dynamic programming to solve the shortest path problem, will fail. So what do I mean by optimal substructure? That's the property that a subset of our optimal solution is optimal on the corresponding smaller problem. For example, if you think of the given numbers here as travel times or distances, the optimal path from A to C is the red path. And if I just take A to B, the optimal path from A to B should still be the red path. So a subset of my optimal red path remains optimal on the smaller subgraph from A to B. Well, this is the property that fails if we want, for example, a mean plus standard deviation objective function. So if we are interested in finding the path that minimizes its expectation plus the standard deviation, with the given numbers here, mean and standard deviation, say of travel times on each edge, we can quickly check that the optimal path from A to C is, I believe, the red one. And from A to B, it's actually the blue one. So let's just make the calculation for a sanity check. From A to B, the top edge, the red one, has mean plus standard deviation equal to 8, whereas the bottom one has 7.9, and so it's optimal to go on the bottom. Whereas going from A to C, we would prefer to go along the red route throughout. So we lose this optimal substructure, and therefore we cannot use the traditional dynamic programming methods and just all the other types of algorithms so far that have been used for solving shortest paths. And again, this challenge is linked to the non-convex, in this case concave objective, that is the mean plus standard deviation objective. So how can we solve the problem in this case, if this is our goal? If our goal is to minimize the mean plus standard deviation of a path, what can we do? So I turned to optimization at the time when I was thinking about the problem, and I saw that, again, not much is known in the area of global optimization. And we had to develop a solution from first principles, and the solution was based on 3 insights. The first insight is that even though if we think of the incidence vector of a path as a vector of having a coordinate for each edge with 1 for the edge which is in the path and 0 otherwise, this vector is in dimension equal to the number of edges. And so if we think of the problem in this case, the objective function mean plus standard deviation is also a function in fairly big dimension of the number of edges, but we can actually think of the problem as two-dimensional because all we care about is the path mean and the path standard deviation, which is square root of the path variance. And so we can just project our entire problem, the feasible set and the objective function, on the mean variance plane. And here the red dots correspond to different feasible paths with x and y coordinate equal to the mean and variance of the path. And let's now understand our objective function, the path mean plus some constant r times the square root of the path variance has level sets that are parabolas. Level sets are the curves where the function, the objective function, has the same value everywhere. And they're parabolas that have higher values as on higher parabolas. In this case, we are interested in the minimum mean plus standard deviation path. So we would be interested in sort of the first time a parabola from the bottom hits our feasible set. And so we can see geometrically, visually on this picture, that the optimal solution is this path right here. So this is our optimal solution. This is the path that has the smallest mean plus standard deviation. And so now the...
Unique, right?
Say that?
This doesn't have to be unique.
The solution does not have, yeah. Okay.
Yeah, that's what I asked.
Sure, yeah, it doesn't have to be unique. That's correct, yeah. So we may have one or multiple paths that are optimal. We are interested in one of them. But even if it's not unique, what I want to remark next is inside 3 that the parabolas would necessarily first hit the feasible set on an extreme point of the feasible set. And so the solution must be one of those extreme points. So for example, those paths inside would never be one of the optimal ones, but we have at least narrowed down to the extreme points. And this is, of course, the well-known property of concave functions, that the minimum of a concave function is attained at the extreme points of the feasible set. And so that immediately suggests one algorithm. If we want to find the optimum, enumerate all the extreme points and evaluate each of them at our objective function and pick the best one. And this is, as far as I know, the state of art in concave minimization. We don't really know for general concave minimization what else to do, what better to do. And so we can enumerate all the paths, but of course, algorithmically, immediately we can ask what is the complexity of such an algorithm. It depends on the number of extreme points, and if there are many, that would lead to a very inefficient algorithm. Well, in the case of shortest paths, it turned out that they are not so many. So there is an exact algorithm that goes through the extreme points, and we don't necessarily need all the extreme points. So I didn't mention here that we only need extreme points on the lower left of the feasible set. And this is important because those extreme points here correspond to longest path instances, which we do not know how to find algorithmically. But those extreme points here on the lower left we can find because, for example, the lowest point corresponds to the path with smallest variance. And so since variance is, as I mentioned earlier, an additive problem, we can find that with a deterministic shortest path algorithm with respect to variances as the edge costs. Similarly, the path on the leftmost there is the path with smallest mean, and again we can find that algorithmically, and similarly we can find all the points in between. So what is the complexity of this algorithm? It is determined by the number of extreme points, which in shortest paths turns out to be n to the log n.
How do you find the points in between? By assuming some kind of combination of various combinations?
Yeah, so there are multiple methods for finding the points in between. One of them is some kind of binary search. For example, start with finding this one, and then draw the diagonal and use that as your next objective for the trade-off. And then keep, that will find this point, and then between this and this, look for the ones in between, and keep going. And so you would require at most 2 times as many iterations as there are extreme points to find all of them and make sure that you have found all of them. There are other algorithms as well. It's an interesting problem in parametric shortest paths, where if you start with this one, can you find the next one and then the next one, so find them in order. That's another type of algorithm, and there are various variants of those. And so again, in shortest paths, the number of such extreme points is n to the log n. That's a really interesting result, actually, from the 1980s. The upper bound is easy to establish. The lower bound is a highly non-trivial graph construction with very carefully determined weights, A and B per edge. And so to this day, our best solution here is an exact algorithm that has a super polynomial complexity. So it's likely not an NP-hard problem, but at the same time, we don't know if this problem can be solved in polynomial time. We have a conjecture whether on planar graphs we can establish that the number of such extreme points is polynomial. Again, we haven't really made progress on that yet. So I just mentioned some interesting problems along the way. This is something that practitioners probably don't care about at all. They just care what is the performance of these algorithms in practice. And in practice, this algorithm was adapted and implemented in actually a real-time traffic project at MIT called Cartel, where they measured textual traffic on the Boston Road network. And with this algorithm, they were able to find various risk-averse, risk-minimizing paths. And they observed that the running time was very fast because in practice, often it just boiled down to enumerating about 10 extreme points between representative source and destination points in Boston. And so I ran also simulations on grid graphs with uniformly random weights just to understand what is the number of extreme points that we may observe. And the results were always very encouraging. There was a very small number of extreme points. And this was confirmed by a smooth analysis type result that we had subsequently, which established that if we perturb the mean variance a little bit, then in expectation with respect to this perturbation, the number of extreme points is very small.
So what's typically the total number of points?
I can just give the anecdotal evidence of the MIT project, which came down to listing about 10 extreme points.
I'm asking about the entire.
Overall, the entire. Well, just take one example. I mean, in graphs, typically all the total number of paths is exponential, right? So you can easily see that in.
You're talking about specific examples in this MIT.
So I don't.
It doesn't look like that.
So that's a typical road network, and now you're asking what is the total number of paths in a typical road network. And again, think of the Manhattan grid. So you can.
Yeah, that has a lot.
Right. So I think in many real-world problems, you would have an exponential number of.
Probably prune almost all of them as being unrealistic.
Probably so, and in fact, the algorithm that was implemented was doing a little pruning in addition to this enumeration. So it didn't just brute force enumerate all the extreme points. It did a little bit of pruning, but still, in theory, with pruning, we cannot prove that we can get something less than super polynomial.
This problem also seems like it should have a polynomial time approximation scheme, right? Because
absolutely. So this is the next thing. So once we have a polynomial smoothed analysis, we can convert that easily into an epsilon. In this case, we got an epsilon additive approximation. With different methods, later I was able to establish a multiplicative 1 plus epsilon approximation. And so indeed, it's possible. And in fact, it's possible to do not only for shortest paths, but for general arbitrary combinatorial problems for which you just an underlying deterministic, an algorithm for the deterministic problem, and you use it as a black box to solve the corresponding risk-averse or non-convex problem.
So this is just for the objective function, which is mean plus standard deviation, or?
So that's why now I'm becoming more vague, and I mentioned risk-averse functions. I was talking about mean plus standard deviation. But we didn't really need anything about mean plus standard deviation other than the fact that it's a concave function. And so its optimum must be one of the extreme points.
You also needed the shortest path. It is for the shortest path.
It was for the shortest path in as much as we needed to find the extreme points. But now what I'm saying is that we can have a generic problem, a combinatorial optimization problem, for which is, let's say it's a minimization problem. So find me a feasible object of minimum cost. So you give me an algorithm for that problem. It's essentially a linear problem, right? A problem with a linear objective. And I say that I can solve for any function which is low rank, in this case rank 2. I mean it's a two-dimensional function, one that can be thought of as 2 dimensions. So as long as it's concave and the optimum is an extreme point, beyond that I don't need anything about the property of the function. The extreme points are completely independent of the function. And I only use the function at the very end. Once I have enumerated the points, I just go back and evaluate my objective function on each of them in order to pick the best one. And so in this sense, the enumeration-based algorithms, they're independent of the objective functions, and they work for any objective function for which the optimum must be one of the extreme points. And the class of such functions is, it includes concave functions, it includes quasi-concave functions, which is a generalization, and various other functions.
So if I just add up things on edges, it should be sublinear. That's concave. I mean, that's any sublinear function of.
If you add up things on edges, you mean?
Have lengths on edges or something. You add a power of those lengths over the entire path. As long as the power is less than 1, it'll be concave, and you can do it.
Okay, so let me just mention, and again, I kept this vague in terms of what risk-averse function, and I mentioned that we can do it for concave functions. So if we want the interpretation of a risk-averse decision maker, what risk-averse functions can we handle? So mean plus standard deviation is one of them. Another one that's very natural is minimizing the probability that you're late, or minimizing the probability that your solution exceeds a given budget. And I'll mention one more after that. And so if we have such a risk-averse objective which reduces to a concave problem, then we can essentially solve this concave problem with a black box reduction to the corresponding deterministic or linear problem. And we would be using this linear problem as a subroutine and invoke it polynomially many times. So this is the theorem. In fact, we can solve the risk-averse or concave problem not only if we have an exact algorithm for the underlying deterministic problem, but even if we have just an approximation algorithm. So if we have a delta approximation for the deterministic problem, we would have almost the same approximation for the corresponding risk-averse or concave problem. And so again, I mentioned the 3 risk-averse objectives that I have thought of so far that fall in this framework of concave minimization are mean plus standard deviation, minimizing the probability that the cost of my solution exceeds a given budget. In routing, minimize the probability that we are late, or minimize the budget such that the probability of exceeding it is at most a given desired confidence level.
If you're using the second criterion, you have to assume something about the distribution.
Yeah, you're right. Yeah, I put the stars here and then I masked the note in the stars. Yeah, so for normal distributions, those come down to, in fact, they become equivalent to concave problems. Thank you. And for other distributions, we can again do some kind of approximation, take Chernoff bounds, and again, we would come down to similar concave problems. So let me go to a challenge of moving to more general risk-averse objectives or more general utilities. So depending on our risk-averse objective or utility, the problem may incorporate longest path as a subproblem and as such be NP-hard. We still can approximate, just for shortest path, we can approximate general non-monotone utilities and again get an arbitrarily good approximation. I'm also interested in moving to a more dynamic or adaptive decision making, and I'll come to that result at the end. But now let me come down to the problem of multiple risk-averse decision makers. So far I said if we have a single decision maker who is risk-averse, what are the algorithms that this decision maker can use to find the solution they need? Now, if again we think of the context of transportation, if I give every risk-averse driver the same outcome and they go through that route, they congest the route, that will not be very good. So we need to adopt a game theory model to take into account the interaction between multiple drivers or the effect they have on each other. And this is the well-known example of Bayes paradox, which I don't have time to go through, but I'll just mention, is the paradox where adding a road can sometimes increase congestion, can lead to more traffic. And this is linked to this concept of price of anarchy that has become very predominant now in the study of algorithmic game theory in many problems. The price of anarchy measures the degradation of system performance due to selfish behavior. Or a little more precisely, it measures the ratio of the cost that we experience in the worst Nash equilibrium, that is when players play their individually optimal strategies and reach a Nash equilibrium, versus the cost in the system if a central decision maker, a central coordinator decided where everyone should go. And so this price of anarchy I'll just mention was measured to be, analyzed to be 4/3 in general graphs with linear latency functions that indicate the functions of the travel time as a function of number of users or flow on the edge. And so I started the talk by saying that the main thesis of the talk is that risk and uncertainty can dramatically change system performance and the properties of resulting equilibria in this case. And so here, what I want to demonstrate is that in a particular model of uncertainty, various risk-averse preferences may lead to very different types of price of anarchy. So I will not go into the different definitions here, but I just want to mention that under various risk-averse models, we can have anywhere from a small constant price of anarchy to unbounded price of anarchy. And again, price of anarchy measures the degradation of system performance due to selfish behavior. And so we conclude here that the modeling of risk and uncertainty can very critically affect our prediction of system performance. And thus, it should really be taken into account when we're thinking of system design as well. And this work is just one of now a growing number of works or research on risk aversion in routing games. And to zoom in a little more into one of these models, our goal... What's that? That's what happens when you run the algorithm. No. It's just another picture to bring your mind back to transportation and the challenges of congestion. So we want to understand the effect of risk itself on congestion. So how much we know that selfish behavior leads to some congestion in the sense of increased overall system cost. But now can we decouple just the effect of risk-averse attitudes from that of selfish play on congestion? So that is our goal here. And so in a sequence of papers, we analyze various properties of equilibria. And then we came up with this new concept of price of risk aversion, which I felt bad since there are so many price of X, price of Y, and so on. In the field of algorithmic game theory, we have price of anarchy, price of stability, price of coordination, and so on. So I felt guilty for introducing yet another notion, but we couldn't come up with a better name. So this simply refers to the price that society has to pay in increased congestion or increased system cost due to risk-averse attitudes of the individual players. And so our model is just a natural generalization of the classic game theory model of routing games or congestion games, which is we are given a directed graph with the general model has multiple source destination pairs, but in this one we just look at a single source destination pair. And we think of the players as small particles of a flow, so it's a non-atomic model. So the players are infinitesimally small relative to the whole population. And each player wants to get from the source to the destination via a certain path. So their strategy set is the set of available paths from S to T. So we can encapsulate the strategy, the resulting decisions of players as a flow vector in the space of all paths. So we would have one coordinate for every path, which tells us how much flow is routed along that path, or how many drivers choose to go along that path. And in classic congestion games or routing games, we just have a latency function or edge delay function, which is a function, LE, of XC of the flow on the edge. Now we want to introduce uncertainty, and so we say we can think of this as the expected delay. And we have noise additionally. We assume independent noise across the edges. And so the noise here is just some random variable with mean 0 and some given standard deviation, which again may or may not depend on the flow on the edge. And so now, again, for the sake of starting somewhere, we assume that the players want to find minimum risk paths defined by the mean standard deviation objective. We also look at the mean variance objective because it's easier computationally and for the sake of comparison. So again, in mean standard deviation, everyone wants to minimize the mean plus standard deviation on a path. And in the mean variance, players instead want to minimize the mean plus variance on a path. And remember that in the mean variance objective, things are additive, so computationally they are easy. We can find the minimum mean variance path easily. So I should tell you now what is the notion of an equilibrium. This is the natural generalization of Nash equilibrium, which is known as Wardrop equilibrium in the context of congestion games. Wardrop, I believe, defined the concept almost at the same time when Nash was defining the Nash equilibrium. And so the equilibrium simply is a set of paths, one for each player, such that nobody has incentive to deviate. So no one can switch to a path with smaller cost. And by cost here, I think of the mean standard deviation cost or the mean variance cost, but of course the equivalent definition holds for any other risk-averse definition. And I'll differentiate a little later on between a risk-averse equilibrium and a risk-neutral equilibrium. So this is the equilibrium where the cost here is just the expected delay of the path. So I'll just mention very briefly, since I'm running out of time, that we characterize, first of all, the existence of equilibria in this model, in the mean standard deviation model. That's the more challenging model. And immediately we see in the classic model, we have a small convex program, so the equilibrium can be found computationally. Here, sometimes it's a convex program, but it's exponentially large, so we cannot necessarily solve it quickly. And sometimes there is no equilibrium. Furthermore, another challenge is that if we happen to magically find the equilibrium in terms of how much flow should be routed along each edge, and we now want to decompose it to say how much flow should go on each path, this is a non-trivial problem. Not every path flow decomposition of a given edge flow equilibrium vector is an equilibrium. Nevertheless, we can show non-constructively that an equilibrium or a socially optimal traffic assignment, there exist equilibrium and socially optimal assignments which use only polynomially many paths, but still we don't know how to find them. And in terms of price of anarchy, we understand what happens when the standard deviations are constants on each edge. They don't depend on the flow. It's the same as the deterministic price of anarchy, the corresponding results for the deterministic games, but we don't know what happens for non-constant standard deviations. But now again, I want to come back to this question of decoupling the effect of risk from the effect of selfish behavior in terms of contribution to overall congestion or system cost. And so we define this concept of price of risk aversion, which measures the ratio of cost of risk-averse equilibrium to cost of risk-neutral equilibrium. So if everyone is risk-averse, and that's how they choose their route, how much more would they travel relative to if people didn't care about variability and risk? And here is one toy example just to build a little intuition. If we have a choice of two routes from S to T, one unit of flow that we need to route across, and we just need to decide how much flow x should go on top and the remaining 1 minus x to go on the bottom. If we have the corresponding mean variance parameters over there. So here k is just some parameter that I've chosen, and there on top I've postulated that the mean is a function of the flow x. It's the flow x times some 1 plus rk, where r is my risk-averse coefficient. Yeah?
The welfare is still the risk-neutral welfare. So when you're talking about cost of...
Thank you. That's a real critical question, and I kind of swept it under the rug here. So for the purpose of this slide and coming slides, the cost of a flow will be with respect to risk-neutral users, and we justify it by saying it makes sense from the point of view of a central planner who cares about long-term averages. And so the cost of flow is just the sum of expected travel times. So in the cost, we don't factor variance. And that way, we can also don't compare apples and oranges, but we compare both flows with the same.
So then is it clear that this is always greater than 1? Or
It's not necessarily. So sometimes risk-averse attitudes may help reduce congestion. So that's an interesting question. We haven't focused so much on that. We wanted to see if it hurts, how much does it hurt? And so in this case, I just want you to notice that if my objective function, and here I'm switching to a mean-variance objective function. So users want to minimize the mean plus r times the variance. So r is some risk-averse coefficient. So on the bottom, they will face a cost of 1 plus rk. On the top, they will face 1 plus rk times x, which is less than or equal to 1. So risk-averse users will always face weakly lower cost on the top. So all risk-averse users will route on top. So when risk-averse users route on top, this x becomes 1, and they will experience a cost of 1 plus rk. Risk-neutral users who don't care about the variance will route on top and on bottom. And in equilibrium, the top and bottom will have equal expected delay, which will be 1. So the cost of risk-neutral users will be 1. And so this ratio, how much more do we travel in a risk-averse equilibrium, will be 1 plus rk over 1. So the price of risk aversion, this ratio, will be 1 plus rk. So again, k here was some arbitrary parameter that I set for the variance. R is given by my input, the degree of risk aversion. So people care to minimize the mean plus r times the variance. And so as you see, with k growing large, this ratio may become unbounded, which is not a very interesting, and it somehow is very pessimistic prediction that risk-averse users may travel arbitrarily long more than the risk-neutral users. Well, in practice, it is natural to assume that the variance is not too much larger than the mean. this is captured by the mean to variance ratio. So if we assume that the variance to mean ratio is at most k, some given k, then in this case, the price of risk aversion is 1 plus rk for this k. And this was for this very simple network for a very general, for a general graph. What we were able to establish is that the price of risk aversion is at most 1 plus rk times an additional eta parameter, which depends on the topology of the network. And in the worst case is n over 2, the number of vertices over 2. And I don't have time to go over the details of the analysis, but I'll just mention that the analysis is very different from the classic price of anarchy types of analyses. And most notably, the result depends on the network topology. So the price of anarchy result, which I mentioned, price of anarchy is 4/3 for all graphs with linear latencies. That is a constant for all types of network topologies. Here, if the graph is series parallel, eta is 1. If it's the brace graph, eta is 2. But in the worst case, it can be as large as the number of vertices over 2. We have...
Even the price of anarchy is
you're correct, yeah. For series parallel, the price of anarchy is actually lower. And so that actually is because of a different perspective of how to analyze these system losses or the system degradation. We have a different type of analysis, which is, I guess, more in line with the traditional price of anarchy, which says that the price of risk aversion is at most the price of anarchy inflated by our risk coefficient. So let me, yes, here we assume that all players are risk averse with the same R. So they have exactly the same risk attitudes. Subsequently, we were interested in finding if heterogeneity of risk preferences leads to lower system cost, which it sometimes does and sometimes doesn't. So diversity doesn't always help in this situation. But most importantly, I really want to extend all of this research to dynamic models or adaptive models. First of all, for routing, if we can adapt on the fly.
Way beyond.
Oh, we're way beyond. Sorry, yeah. So yeah, let me conclude here that basically the goal is to develop an algorithmic toolkit for risk mitigation in networks, and we have a lot of open problems. I hope I have convinced you that we may need fundamentally different approaches in both algorithms, game theory, and mechanism design. And ultimately, I hope that this theory will have impact in various application domains, such as transportation, smart grid, and so on. Thank you very much.
Any questions?
Could you go back to the slide, which I think you skipped on the open? Would you be willing to say a word or two about that?
Of course, yeah, of course. So in the algorithmic part of the talk, the first part of the talk, I only spoke about static models. So here is the graph, here is the information that we have about random variables, parameters, and so on. What is the shortest path? And I would love to develop a more dynamic or real-time decision-making framework. And there are different types currently in the algorithmic community. There are different types of dynamic. One is that of the framework of online algorithms or online learning. Another one is that of adaptive dynamic models in the Markov decision process style. So the first one is for shortest paths again. If I need to take my route to work every day, I observe what happens on the previous days. Can that somehow inform me on my route choice today? And because of risk-averse attitudes, how does it change existing online algorithms?
Can you actually explain that there are a lot of, there isn't one player here, right? There are a lot of players.
So I keep switching back and forth between the single player and multiple players. This, I'm only thinking about single player so far, but you can also think about a game theory that
if they all do exactly the same the next day, then
yeah, here I'm not thinking about the game here, so I'm thinking simply about the computation of the optimal path. adaptively, if we think like a Markov decision process, so here my shortest path is a strategy, how to go from here to the airport. I want to arrive there on time, and I can adapt my routing choice at every intersection, at every node. How do I do that if I have a risk-averse utility function? So this comes down to risk-averse. It's related to risk-averse Markov decision processes, about which very little is known. Convex risk measures. So I didn't mention that the earlier results I mentioned that were related to concave minimization were possible because the problem was concave. And if the objective was instead convex, which we think of as an easier problem, convex minimization is actually harder on combinatorial problems because the relaxation of the convex problem may fall on a vector that's not a valid path. It may be a convex combination of paths. And so we don't really know how to solve convex minimization problems for combinatorial feasible sets. So this is what I mean by this bullet. And again, going to game theory and mechanism design, you can extend all of these and beyond. So
this is a vague question. It seems like if there's a benevolent central entity, it should be able to incentivize people so that the price of risk aversion is avoided by paying people if they lose because of the risk and taking money from people if.
So that's an excellent question, and that's what I mentioned at the very beginning. There is a very elegant theory of optimal tolls, which says that if we compute tolls, the toll comes down to being the derivative of the latency function on every edge. So if we charge those tolls so that users face this latency function plus the toll, then selfish players who play according to these updated latency functions will actually reach the socially optimal traffic assignment. And this is the mechanism design in this case is this set of tolls. But if instead travel times are uncertain and we have those risk-averse routing choices, we don't really know what happens to this theory doesn't hold anymore. And so is there an equivalent theory that has, again, optimal tolls that are edge-based, or do we need a toll which depends on the path choice? Maybe we won't be able to decompose things into edges because of the non-linearities, so we don't really know. So this is something that I'm currently working on.
Maybe just comment on the prevalence of Bayes paradox in risk-averse travelers. Is it? I mean, okay. So it's a generalization. So every case that's going to have Bayes paradox before is going to have one here. But do you think it's going to make Bayes paradox significantly worse? That it's going to be more prevalent because of this?
It's also a really nice question on Bayes paradox, and would we observe it again, and would it be worse or better? And so in this work here, where we considered heterogeneous risk attitudes, where players minimize, again, mean plus R times variance, but different R's for different players, we noticed a connection with Bayes paradox, although it was not a one-to-one connection. So in instances where there was Bayes paradox, we observed that diversity would hurt, and the other way around. But it wasn't a one-to-one correspondence.
But take further questions offline because break is getting shorter and shorter.